today's boarding session is seismotectonics and TNDS of both countries. The chairperson of this session is Professor Mike Sir. I would like to request him to come dance. And co-chairperson is Dr. Suresh Givire. Reporter is Narayan Krishna Ganesh. So we will have altogether 10 presentation in this session, and then at 11 o'clock we conclude this session. Now I would like to request Mike for the session. Thank you.
Thank you very much for tribute to some of the major geologists that we've lost. And I would just like to make a mention of Paul Tappanier and Peter Molnar, who are two of the great figures of Tibet Himalaya geology. Peter Molnar had we made a small speech about him in the last HKC. There's another person, Ann Yin, from California in the US, who also died recently, very prematurely. And he was a tremendously influential figure in the Western Himalayas in particular, and in Tibet, and all over continental tectonics of the US. But we're going to start off today with Somnath Satkota, who was a student of Paul Tappanier. And Somnath?
Yeah, I am here.
Where are you? Please, over to you.
Thank you. I work with the Paul since 2008 actually, and I have two personality here, Naram Bolanje and Pradeep Perrier. He is also here who make me to connect with the Paul Tappanier in 2007. Next. So, brief introduction. Paul was born in Annecy, France on January 6, 1927. Paul Tappanier was first and foremost an extraordinary geologist and observer of nature. He had an exceptional talent of first reading the record of history on crustal information in landscape and in the rocks, and explained his views in a simple concept. He pioneered the use of satellite imagery to map active faults and to produce the first comprehensive map of active faults of Central Asia. Based on his map, he proposed that Tibet was being pushed towards as India is intending into Asia. He developed the models of the India-Asia collision using analog experiment and more recently numerical modeling. Through extensive collaboration with the geologists from China, Nepal and other countries in Asia, his work led to the quantification of quaternary fault rates in the Tibet and neighboring region. Based on his analog experiment and his geological observation, he proposed and demonstrated that the successive extrusion of the continent block both accommodated and the convergence between India and Asia and were associated with the opening of marginal basin. He also documented structure of the number of recent large earthquakes, including in Nepal, and discovered evidence of major past earthquakes on a number of faults at the piedmont of the Himalaya. He worked in Assam also. Beyond Asia, Tappanier clarified rift propagation, earthquake return times, and tsunami sourcing in Afar, Mediterranean region, Indonesia, and North America. These ideas and methods had enormous influence on our understanding of tectonics. Next. Paul Tappanier graduated from the prestigious École Normale Supérieure de Mines, the Paris, in 1970. During his training, there he developed a passion for geology that devoured him his entire life. After a thesis at University of Montpellier, in close cooperation with Maurice Motter and including the history of 1973 to 75 at MIT with Peter Molnar, he moved to the Institute of Physics, the Globe, the Paris IPGP, where I have done my PhD, and he founded the Laboratory of Tectonics and Mechanics, the lithosphere. He took part in the first field expedition in Tibet, revealing his talent for reading the sign of active tectonics in the landscape. In 2009, he went on an international career first at the Earth Observatory of Singapore, and in 2019, and the National Institute of Natural Hazards in Beijing, fluent in French, Italian, English. He also learned basic Chinese. Paul was a real cosmopolite, curious of all aspects of Korean culture, and food and literature in particular. Next. He was honored by many awards like the silver medal of the Central National Dala Research Scientific France, Alfred Weiner Award of EGU, the Grand Prix Dala Ville of Paris, and Fellow of American Geophysical Union, Francis Lecturer of American Geophysical Union, Lead Medal Geophysical Society of London, member of the French Academy of Sciences, 2005, corresponding member since 1994, foreign member of US National Academy of Science, honorary fellow of Nepal Geological Society of London, and Einstein Professor of the Chinese Academy of Sciences, honorary member of Nepal Geological Society, promoted to the rank of Chevalier of the French Legion of Honor in 1996. This event France Award of the Chinese government in 1998. Next. He came to Nepal to find some surface rupture of many big earthquakes in the Himalaya. So we worked with him with these three research interests. Next. First time, Salman Upreti sir, our professor, and Laurent and Frederic Perrier. Frederic Perrier also is not with us. And he came to Nepal and we had kicked off the meeting in the historical archaeologist at the Shankar Hotel with the DMG. And then from then we are starting and we are scouting along the main frontiers of the Himalaya. Next. So during what is the pole contribution in Nepal Himalaya is first Nepali PhD student under the collaboration framework of DAS DMG. It was mandated from the DAS DMG collaboration with the Laurent Valentin and Frederic Perrier. And then he moved to Singapore on 2009 and he started to collaborate with DMG by signing the MOU with DMG. Then altogether he made 7 field trips, 7 sessions. We conducted the 7 sessions of the field trips mainly in the MFT from east to west. And first discovery of surface rupture 1934 and 1225 earthquake in the foot of Himalaya is published in the Nature Geoscience. And paleoseismological trenching uses different mapping tools from total station to airborne lidar. Understand the limitation of trenching in Nepal Himalaya. There is a limitation of trenching in Nepal Himalaya. Involved in the efforts of monitoring after 2015 earthquake, deploying some temporary stations and seismic diffraction survey to locate the subsurface information around MFT using active source. We have done the active source. And we have viruses, many were key to make the seismic that's inactive seismic survey across the MFT. And a core recovery drilling in hanging wall and footwall of the MFT to make the precise location of the MFT in the Bardivas. And published more than 12 research articles in the MFT region. More than 12 research articles in international journals like Nature, Science, Geology, Technology, Physics, all kinds of planetary science, and JGR, and so on. Develop a hypothesis in Nepal Himalaya that slip along the MFT in every 600 years from the uplift of the river terraces by getting the terraces technique. We can talk like 2 hours in these topics. So I just mentioned it here. We need to expand laterally his hypothesis. What we have to do now is what we are tested in the central part where 1934 earthquake most affected area. Then to the eastern, this laterally we have to extend his idea to laterally. His beloved wife Kevin photographed his work and published a documentary called Quest for Quake. You can go to YouTube and have a look on it. The Quest for Quake is very simply written next. Some photograph. This is the honorary membership of the Nepal Geological Society from Ramdharan, our president Ramdharan Yadav. Next. You see, we have started from total station to airborne lidar. During our study, we have done to map the fault in the front. Next. So these are some photographs of the core in the field. I know is along with the cultural things in the village. Next. So this is the biggest and best trench we open in the Himalaya. So still we not with the single earthquake. That's why we still that idea of the mega trends. Next. So this is the way we miss you, Paul. Rest in peace, and we will be always guided from you, your spirit and love. Next. Okay, this is a great loss of the geoscientific community globally and Himalaya Tibet region in particular. We will keep following you in your ideas in the days to come. Thank you.
Okay, thank you very much, Tom. That was excellent tribute. We'll go straight on now to Dr. Adhikari, who will continue with the other people in the program.
So we can continue with the tribute to our legendary geoscientists who are the life member of Nepal Geological Society. Last 2 years, we lost several life members of the Nepal Geological Society. With deep respect and heartfelt gratitude, we remember these extraordinary professors and professionals in the field of earth science. They ignited a curiosity in us that has stayed with us throughout our lives. They fostered environments where questions were encouraged, explorations was valued, and the pursuit of knowledge was always at the forefront. So we will next. The seven life members of Nepal Geological Society that we lost in last 2 years were Vishwaman Singh Pradhan, Prakash Das Gulab, Nagraj Shrestha, Jitendra Gujare, Ram Nagina Yadav, Perry. Vishwaman Singh Pradhan, he was born in 1931, December 5, and passed away in 2023, August 27. He was the honorary member of Nepal Geological Society and honored in 2005. He is the first department chief of the Department of Geology in the campus who started the geology study in Nepal. Especially he used to teach crystallography and mineralogy. He did his masters from the University of New Mexico, USA. Next. Prakash Das Gulab, he is also associate professor. He was also associate professor in Chandra College. So he was born in 1963, April 17, and just passed away 30 October 2024. He did his PhD degree in geology from Shimane University, Japan in 2006, and the work was on evolution of fluvial system of late Cenozoic Geologic Group Nepal Himalaya related to tectonic of the Himalaya and climate change. He is one of the very few geoscientists working in the Shivaji in Nepal. Next. Nagraj Shrestha was born in 1952 May 10 and passed away in 29 December 2023. He did his masters in geophysics from Banaras Hindu University. He was specialized in exploration geophysics. He is the former superintendent hydrogeologist at Department of Irrigation in Nepal, and after the retirement, he had his consultant, and he was managing director and CEO at that 3D consultant private. Next. Jitendra Gujare, born in 1950, March 22nd, and passed away on November 3, 2023. He did his master's degree in applied geology from India and engineering geology from USA. He was joint secretary at Ministry of Water Resources. He was the Director General of Department of Irrigation. NGS had honored him with Lifetime Achievement Award in 2021. He is one of the pioneers in the development of groundwater exploration, exploitation, and management in Nepal. Next. Ram Nagina Yadav. So he is one of the oldest first member of the Nepal Geological Society, last member of the Nepal Geological Society. He is well-renowned senior geologist and retired from the Department of Mines and Geology. Next. Frederick Perrier, he is also the life member of Nepal Geological Society. He is from France and he born in 1961, August 22, and passed away in 2024, November 21. Just almost 1 or 2 months before he left Kathmandu, before he passed away. He was in Kathmandu for 3 months. And Frederick Perrier was born in Alais in France. So he worked in a high energy physicist from 1981 to 1992. Then he joined last CA, with which we have a collaboration since the last 40 years, more than 40 years. And he worked there from 1993 to 2003. From 2004 to 2023, so he was a professor at IBGP in Paris. He launched the PhD thesis of four Nepali researchers and one master's thesis. And he could speak more than 8 languages, including Tamil, Nepali, and others. And his main by the time, so at this time, his main area of research was autistic in Nepal, also and carbon dioxide emission in Nepal and the world. So he is also Vice President of Swiss Foundation, and since 1997, this foundation has financed the large ongoing school, largest ongoing school and medical care project in Nepal, in Gokha. So he used to visit every year, either one time or 2 times in Nepal since last 30 years. So I conclude our tribute to the legendary geoscientist. So now I would like to request all the audiences for 1 minute of silence. Start.
Very much. That's very well presented. We're going to move straight on now to our keynote lecture.
So today I will focus my talk on some of the researches we conducted after the Gorkha earthquake within the framework of the long-lasting DAS-DMG collaboration. So my institute has a very long-lasting collaboration with the Department of Mines and Geology that began in 1978. So I won't speak about all the researches conducted since 1978, but we focus my talk on some of the research we did, particularly on what we did within studies of the regional seismicity below the stations we deployed in Nepal. So as you all know, Gorkha Nepal earthquake in 2015 is the latest of a long list of devastating marine earthquakes which happened on the mainland thrust, the plate boundary fault between India and the Himalaya. And so these devastating earthquakes, or large or great earthquakes, rupture partially or totally the uptip segment of the mainland thrust, which is locked from the surface down to mean-crystal depth of 15 or 20 kilometers at the top of the greater Himalayas. So any information on the seismological segmentation of the fault system at depth is fault may help better constrain the relative frequency of the large and great earthquakes. Their help tackle their maximum magnitude as well as the associated seismic hazard. So it's our motivation to better understand that. And so the mechanical simulation reproduced quite well the bipodal seismicity with sometimes large earthquake, blind earthquakes clustering at the down end of the mainland thrust, and sometimes larger ones rupturing up to the surface. And so this bimodal seismicity is mostly controlled by friction variations and or non-planar geometry of the mainland thrust. So the question we were facing is whether we see the signature of the structures at depth or friction variation in Nepalese microseismic pattern, or within the behavior of this microseismic pattern. After the Gorkha earthquake, along the rupture, before the Gorkha earthquake, or at other places in Nepal. So to answer this question, we used the seismic bulletin from the National Earthquake Monitoring Research Center, the signals at stations operated by the Department of Mines and Geology and deployed within the DMTS collaboration, which represents a little bit more than 50% of the presentation of the National Seismological Network. And we complemented also these stations with, by a temporary experiment under the French National Research Agency. And in my talk, I will focus first on summarizing results we had along the Gorkha earthquake rupture, then on Far Western Nepal seismicity, and I will finalize my talk with recent results we had on pre-shocks of Gorkha earthquake seen at GKN, which is one of the historical stations of the collaboration, deployed in 1985 in Gorkha, near Gorkha Pass. As you will know, the Gorkha earthquake 2015 happened in April 25. It nucleated below 25 kilometers north of Gorkha, below the village of Barpak. And so the rupture propagated during 50 seconds. It was a unilateral rupture toward the east, from Barpak, Gorkha, toward the east of the Kathmandu Nepal. And the fault ruptured on a surface of about 140 kilometers by 50 kilometers, and the slip at depth peaked a little bit above 6 meters. It's what we know from the inversion of INSA, EPS, as well as the inversion of the waveform of the records at telescopes. So the region north of Kathmandu was uplifted by more than 1 meter, while the long-term range subsided by a meter also. And Kathmandu was translated within 50 seconds by more than 1 meter. So very quickly, the seismologists realized that the rupture only covered half the log fault zone at depth and stopped just below Kathmandu. And so, in the very few weeks following the earthquake, the National Earthquake Monitoring Center already recorded and located thousands of aftershocks, and we noticed at that time strong heterogeneities in the seismic pattern. So these heterogeneities at this time were interpreted as related with the lateral variation of the structural depth of the MHD of the ramp, the Metric-style ramp of the MHD, as well as heterogeneity in terms of orientation of the fault in the hanging wall of the main human thrust, which are stress receiver in the hanging wall, and that were locally producing seismicity. So after 5 years of aftershocks monitoring, the post-seismic pattern was even clearer. So this seismic pattern will be detailed by Longvija Vicari. It was the focus of this, and will also be detailed by Theo Bezu in one of the next presentations. So what we've seen at this time is that most of the aftershocks occurred and at the up end of the tip after sleep, which is represented by the blue lines. So what's interesting, looking into detail at those aftershocks after 5 years, is that so in density map that it reveals very well the long strike heterogeneity that you might see on this map. We got western section producing less earthquake than the eastern section, with clusters of aftershocks happening to the north at the down deep end of the rupture. And so what looked puzzling is that this cluster to the north just depict a very odd pattern, and we've seen that pattern in the years preceding the Gorka earthquake during phases of transient microseismicity. For example, in this area north of Kathmandu, where you see southward stepping clusters, we've seen the same kind of southward stepping at the same places in 1997 between January and February with the same kind of pattern. And so this suggests a control of the microseismicity by the structures at depth. The stressing is not the same at all in 1997 and in 2015. So in fact, we think the complex pattern of the seismicity is mostly controlled by the geology. So I will now focus on the cross-section through Kathmandu and the long tongue. And this will be detailed and updated with more earthquakes by Geological and Geological in this session. But I can tell you for the moment that in this on this cross-section we have a lot of aftershocks at the toe of mid-Poseidon that develops below Kathmandu, and at the very place where the seismic rupture adduced into 2050. So the Kathmandu cluster is a new cluster. We've never seen it in the past, and it revealed additional hidden structure like lava. So first conclusion for the first part of my presentation. So what did we learn from Gorka earthquake? First, the structure at depth. That the structure at depth likely controlled the seismic rupture. I will not take all the results we had on the seismic burst, but I think Geological will detail it. And then, there are implications of it. So the deep segmentation of the fault system likely controls the extent of the rupture of intermediate and or large earthquake in Nepal, so it's worth it continuing working on this. We see the signatures of structure or friction variation in the Nepalese microseismicity or its behavior. One of the questions I was asking at the beginning of my talk. The answer is yes, and there are persistent lateral variation of the microseismicity, which are visible at every step of the seismic cycle in Kathmandu area. Do we see that everywhere is the question I will try to answer looking at the seismicity in far western Nepal. So we had an experiment ongoing during the earthquake in far western Nepal, above the mid-fossil cluster. It's a temporary network we deployed in December 2014, and that was recording the micro-earthquake in the area during 2 years. We covered well the period of stress of the Gorka. It's far from Gorka. The seismicity and the seismicity in the area is quite different than in Kathmandu area. It's more complex with very large lateral heterogeneity. So on the photos you see some of the contributors of the deployment. I've seen conduct in the here this one, and other colleagues. But the session with us in 2014. And so these stations were deployed very close to the local seismicity and above it. And so we have a good constraint on the depth of this microseismicity. And as you see from the color code, so the depth of the seismicity is shallower to the south, near Dai Lake, for example, than to the north. And so the microseismicity plunges toward the north. So I will illustrate that through a cross section which is in dashed blue. So this cross-section has been imaged by Shiva Subedi, which did work on the teleseismic P2S visible function with station of this network and imaged a prominent signal from the Moro. And you see here in the head at the base, from 40 kilometers to 50 kilometers to the north. And mid-crystal low velocity zone at mid-crystal depth around 15 kilometers. Materialized here by the blue overhead, which is related to a decrease of seismic velocity probably due to the shear zone of the main Himalayan thrust and the after presence of mid-crystal fluid, aqueous fluid, or CO2 in critical state. So the microseismicity located by Martin Laporte falls very well in this low velocity zone, so in the vicinity of the main Himalayan thrust. And when you look into more details, just projecting this seismicity on the local geological structure, we see very nice pattern and very nice correlation between the microseismicity and the structure at depth. So most of the microseismic clusters are located at the toe of small ramps that are the same size of the ramp below Kathmandu, sometimes a little bit larger. The ramp below Kathmandu is only 3 kilometers high, the step. And so the ramps in southwestern Nepal just reach 3 to 5 kilometers. And so they may control also intermediate earthquake in the area. And in addition to these clusters at the toe of the ramps, we also have some cluster seismicity in the hanging wall of the mainland thrust. And within that clusters, we have also seismic swarms, long-lasting seismic swarms that occur at the junction between the mainland thrust fault and tectonic slivers in the hanging wall. So we looked with much interest to these swarms, which are not preceded by main shocks, which are very small earthquakes that happen at the junction between the tectonic slivers. And it happened that after relocating this seismicity, that this seismicity migrates at velocity of a few dozens of meters per day. And so this is typical of microscopic seismicity that migrate due to the migration of fluid, for example. And so this is an interesting result. So to sum up the second part of my talk, what we learn from the investigation of Far Western seismicity by the network, we first learned that similarly to central Nepal, micro-earthquakes cluster at the top of the mid-crystal ramps, revealing a pattern of ramps and flats which could control the partial rupture in the region. Earthquake swarms occur also at the junction between the main deployment and tectonic slivers in its hanging wall, and some of these swarms migrate with time and could be related with the migration of fluids at them. So the question now is, do we see that in the vicinity of Gorka earthquake epicenter? And it's a recent question we've tried to answer. And so for that, we went for hunting for hidden events in the seismic signal before the launch. For this, we used the seismic signal at Gorka station. As I was mentioning, this station was one of the first historical stations of the collaboration, deployed in 1985. Now by Gorka Castle, Gorka Palace, you can see here on the ridge. And so from the palace, we see the Manasuli Machuli in the background, and you see also a red star which localized the Parpak village under which the Gorka earthquake recreated. So this village is 25 kilometers from the Gorka ridge. So the Gorka instrument was deployed in 1985 near the shelter in which we had, in which DMG had all these instruments, in a shelter that has been much affected by the earthquake, as you see here, but the shelter didn't collapse, but we made a new one to survive here. In order to preserve the instrument for future earthquakes. So we looked in great details to the seismic records at the station, which is the closest of the nucleation of the Gorka earthquake. And so, after filtrating first the earthquake, we are surprised to see 28 seconds before the Gorka earthquake, a very small earthquake. We've seen it only on Gorka station, so it's difficult to locate it properly. But it's a tiny earthquake, and we are able to determine the distance between the epicenter and the station, looking at the time arrival of the S and P. And so the difference between the time arrival is 2.86 seconds, and assuming that the VPVS of 1.75 and the velocity of the P of 6 km per second what we have in the region, we estimate that this micro-earthquake happened 23 kilometers from the station. So we don't know how to locate it properly, but it's the same kind of distance as the distance of the nucleation point of the Gorka earthquake. So that was puzzling enough to think we had to do better work on the seismic noise at this station before the Gorka event. So in order to track the smaller earthquakes and hidden earthquakes in the seismic noise, we selected all the waveforms of all earthquakes that were recorded at Gorka station since 1994. And so we took all the waveforms, and so what you see on the map here is the Gorka station, as well as all the earthquakes we took into account. So either in gray or in waveform, already detected. We named that templates, the templates of gray. And we scanned the continuous signal cross-correlating with the templates and doing detection of micro-earthquake using these templates, searching these templates in the signal. And we detected hundreds of new events, seen on the. And so the resemblance of the detection with the template are quite nice. You see here in red and blue 2 micro-earthquake less than magnitude 1 that happened with exactly the same signal. So that means that these earthquakes have the same kind of source, seismic source, and they've seen the same kind of propagation. And so when you have such correlation, you can say, only looking at the signal, that the earthquake was so similar that it nucleated exactly at the same point as the template. And therefore, you can locate, making this assumption, you can locate this very tiny earthquake into the seismic. So after doing that, on all the continuous signal we get from 2009 to 2015, we found some microclusters of micro-earthquakes in the signal. And so the latest of these clusters happened between March 20 and April 25. And so what's happening is that in 6 years, we had 7 clusters of micro-earthquakes. So we don't know whether there's a special condition with the Gorka nucleation. We don't know that at all. But in fact, when we look at the location of the template that matched for all the 7 crises, you see them here. So you see that the first crisis is a burst of a few earthquakes that happened in 2009. And so the earthquake that matched occurred all along the western side of the Gorka region. But the last of these clusters, which is the most prominent, that nucleated a few days before Gorka, had always the same signature in terms of waveform. So we detected within that swarm about 30 micro earthquakes with exactly the same noise signal as it was just repeating. So this looked like quite puzzling, and we were thinking it's time to communicate on that. So it's difficult to interpret that properly because, as you've seen, we've had several other swarms in the past, and the relation in the literature is not demonstrated. But what we know is that the template that detected is located here on this cross-section by the yellow star. And so this yellow star is a few kilometers to the south of Barbat. What we know is that earthquake nucleated below Barbat, but we don't know exactly at which depth, because it's very difficult to work on that subject with the signals we have. So we don't know whether the earthquake nucleated on the upper décollement, a few kilometers from the micro-earthquake swarm, or whether it's located at the top of the run, which is just below the area where we have this micro-earthquake repeating, or whether the cluster of micro-earthquake happened at the junction between the active décollement and the active ramp, and the Gorka earthquake nucleated on what we name in structural geology the passive roof crust, and then propagated to the south. So we have several models for explaining the succession of earthquake in the area. And so we suspect that all this happened during a transient fluid migration at depth and or a transient slip event on décollement, but we were unable to demonstrate that far. And so this occurred within the weeks preceding. The pattern of seismicity is mainly controlled by structure at depth within the image shear zone, in particular in the vicinity of mid-precise ramps, revealing ramps and flats. In the angle of the décollement, activating contacts in the duplex. Earthquake swarms happen sporadically. Such transient seismic bursts could be related with the presence of fluids percolating along the fault, the active fault, the passive fault, the inactive fault in the angle wall and so on, which are defaults in the geological media. And so this seismic swarm could be related to episodes of local transient straining and stressing. And what we've seen is that there was a swarm of weakening micro-earthquake that happened within the weeks that preceded the Gorka earthquake at a short distance from the center. So researches of similar repeating earthquake swarms should be undertaken systematically to see whether it's just pure high or low probability patterns of emission with the trigger of the earthquake. So future advances of our understanding of the seismicity will certainly come from a better spatial temporal resolution of the local seismicity, leading to a better understanding of the geological control of the seismicity. So we think that for better assessing the seismic result, we need both works by geologists, by seismologists, together to better understand the geological So thanks to the Department of Management Geology and thanks to my department and the French Research Agency for allowing this research funding 3 PhD about 3 PhD, including Le Bizet PhD, postdocs, copyright engineer, master students. Thanks to all the staff at DMG, in particular to the analysts which pick more than 300,000 seismic phases. Thank you all.
Thank you very much, Laura. So we have time for one quick question. Anything else over here?
Thank you very much for your nice presentation. I have just only query. In cluster pattern you could have the depth of width in main event, main cluster and main event. more deeper than the middle part around north of Kathmandu. It may be the MFT structure or other mechanism to happen, but depth variation in different pattern.
Thank you for this interesting question. So it's a tough question because in fact all earthquakes, all aftershocks were not located with the same resolution in terms of capacity to resolve the depth. The depth is very hard to resolve properly, even with the national network. So I know that you worked on the temporary experiment with denser network in the area, and so I suspect most of the earthquakes you located are truly related to processes that happen at depth. But in the catalog of aftershocks, what we get is that sometimes we have a microseismic cluster a little bit below the main domain for theoretical location, but it's not a big deal because we have a lot of uncertainty on the depth distribution related to the unknown we have on the relation between VPS, the velocity model. And so we were able to correct a little bit the depth of the seismicity. We know that there are also uncertainties associated to the structure at depth, and so we've decided not to play with that, to avoid doing some, biased analysis. We just decided to show the best catalog we have with the pattern of faults at depth, knowing that the reality is probably different. But,
Okay, thank you very much, Laurent. We're going to move on to the next talk now by Bin Zhao. And this is on the recent normal faulting earthquake at Pingri in South Tibet.
Bin Zhao from Institute of Seismology, China Earthquake Administration. I'm honored to be here to give this work on to give this talk on work. The title of my talk is Recent Normal Faulting Earthquake Sequence in Injured South Tibet, and its stress linkage to the 2015 Oaxaca Nepal earthquake. Recent GPS velocity is showing the left hand shortening between the Indian plate and Asia. The convergence region is as large as 20 millimeters per year, the southern Tibet is reached by crustal extension in east-west direction, especially across several north-trending river systems. So as a result, there are many normal faulting earthquakes in South Tibet. This figure shows normal faulting earthquakes measured by INSAR data since 1993, which occurred in South Tibet. It's very interesting that after the 2015 Oaxaca earthquake, many almost magnitude larger 5.4 normal earthquake occurred in this region, occurred in the region. So the deep earthquake sequence began with the 2015 earthquake. The magnitude is 5.6. This earthquake occurred just 3 hours later after the Oaxaca main shock. It is followed by the 2016 5.5 earthquake and the 2020 magnitude 5.7 earthquake in the south. And the largest one is the earthquake magnitude 7.0 that occurred on January 8 this year. These are very powerful technology to measure crustal deformation associated with earthquake. seismic displacements for during earthquake sequence well recorded by ESA. Panel A shows the co-seismic formation measured by ESA. It's the level set direction displacements, and the smaller panels are ESA recorded co-seismic displacements for other smaller earthquakes in region. After the 2015 earthquake, my colleague went to the epicentral area and conducted GPS tagging surveys. This figure shows the GPS measured co-seismic displacements associated with the 2012 earthquake. From this figure, you can see that GPS stays in the west of the fortress, the red line, each moves westward. GPS stays in the east of the fort, each moves in opposite direction. You can see some stations at the north side of the fort. The GPS station moves to north, indicating that the rupture terminates at this latitude. In the next step, we first determine the water geometry of the earthquake sequence, and we then multiple co-seismic slip distribution from geologic data. This slide shows the modeling results for the 2015 earthquake. The geometry parameters were not well constrained. The first geometry for this earthquake, the floodplain dips east, and the peak slip, inverted peak slip is 0.2 meters, which occurred at a depth of up to 14 kilometers. And this is the slip distribution for the 2016 earthquake. This floodplain also dips westward, and the peak slip is 0.5 meters. The maximum slip occurs at a depth of 5 kilometers. This is the 2020 earthquake. Different from previous earthquakes, the floodplain of this earthquake it dips northwest, and the peak slip reaches 0.6 meters. Maximum slip occurs at a depth of 3 kilometers. We inverted the co-seismic slip distribution for the 2012 earthquake. It was jointly inverted from both GPS and INSA data. From this distribution, you can see there are two distinct asperities we insert. There is earthquake erupt to the surface. All model in the first order, it fits the GPS data and the INSA data well. We plot on the earthquake sequence together. This is the distribution of the co-seismic slip model. You can see that these four earthquake units are close to each other. And in the first order, the earthquake degrades northward elevation to north with overtime. This is the 2015 earthquake, and this is the 2016, and next is 2020 in this case, and this is the largest one, 2025. One of the intuitive question is that the earthquake is closely related to preceding earthquake, especially to the Oaxaca earthquake. To answer this question, static stress changes imparted by preceding earthquakes, including the Oaxaca earthquake and the transient stress changes imparted by the post-seismic information following the earthquake are investigated. This slide shows the stress changes induced by the 2015 Oaxaca earthquake. The right four panels show the floodplain stress changes on the floodplain or 2015 to 2020 the earthquake sequence. The rest shows that the Oaxaca earthquake increased stress changes on the ruptured floodplain for the earthquake sequence by 10 to 15 hectare. This slide shows the stress changes induced by the 2015 earthquake. For the 2020 earthquake, the slightly the full stress changes is relatively small. It's only 2 hectare, and the stress also decreased on the 2015 floodplain or the 2015 earthquake at up to about 20 hectare. The positive stress change only occurred at various saddle depths at the end of the border floodplain. The stress change induced by the since 2020 and 2015 rupture zones are very close to each other, so the cool stress changes calculated on the 25 floodplain the cool stress change is very large. It reaches over 150 hectare. Besides the co-seismic stress interruptions, we also investigated the post-seismic information. The post-seismic stress changes through the after-sleep or the floodplain or the floodplain, and the visual elastic reaction in the lower cross and the upper mantle. To calculate the post-seismic stress changes, we use the prefix after-sleep model and visual elastic reaction model. This two models have been published in this work. This is my student, and in this model, GPS both in source divided and report are used to construct the post-seismic models. Calculations show that post-seismic changes vary through stress, cool stress, vary the cool stress on the nearby floodplain. Especially for the 2025 earthquake, it increased by 10 hectare, which contributed by post-seismic deformation. So this is a very short story about the earthquake. This is a brief summary. A sequence of number 1 earthquake has occurred in the South Tibet after the Oaxaca earthquake. The first one occurred only 3 hours after the earthquake. The 2015 earthquake was probably dynamically triggered by the Oaxaca earthquake main shock. And the Oaxaca earthquake increased the cool stress changes on floodplain or the earthquake sequence by 10 to 15 hectare, and the post-seismic information also contributed to the cool stress changes by up to 10 hectare. And the 2020 earthquake induced a large magnitude stress changes on the fault plane or the 2015 earthquake. So in brief, although I don't have definite conclusion whether the earthquake sequence is directly triggered by the Oaxaca earthquake, but I think there are some clues and evidence, some of it related to the Oaxaca earthquake. This is my talk. Thanks.
Thank you very much. And now, next talk, we have time for one quick question. Yes.
Gorkha earthquake occurred, thrust fault system and Dingri sequence characterize normal faulting. So, what do your findings suggest that the role of pre-existing fault in South Tibet? Dingri sequence characterize normal faulting. So, what your findings suggest the role of pre-existing fault in South Tibet?
I think tectonic deformation, there are many factors. There are several mechanisms have been proposed to explain why there are several rift systems in South Tibet. I think the tectonic loading is the primary reason for the normal earthquake in South Tibet, and the Oaxaca earthquake and preceding earthquakes may impart stress changes that will accelerate or delay the occurrence of the earthquake. I think this is a secondary reason for the occurrence of the earthquake.
Okay, we're going to have to move on to the time constrictions. Thank you very much indeed for that. The next talk is by Theo Besson, 10 years of Gorkha earthquake aftershocks.
So I'm Theo Besson and I work in the Department of Mine and Geology, and more specifically the National Earthquake Monitoring and Research Center here in Kathmandu. And my work here consists in helping to maintain and develop the seismological workflows of the seismological centers, and to work with my Nepali colleagues to research and development project. And today I would like to show you one of these projects by looking back at the 10 years of Gorkha earthquake aftershocks. So I will focus on the relocation process and the evolution of the seismicity rates. So as it has been introduced, the Gorkha earthquake was the largest earthquake since 1934. And such a large earthquake of moment magnitude 7.8 is expected to generate tens of thousands of aftershocks over years and more than a decade. As the rupture zone is very close to Kathmandu, it's very important to have a close monitoring of this seismic crisis, to give insights of this crisis to the authorities, but also for research purpose, to confront the location to the geostructures. So previous studies have examined up to 5 years of aftershocks, and it was done during the PhD work of Geological. But carry on. So I was saying that the main result of this study is that for the seismicity rate in 2020 it was 7 times higher than the interseismic rate, so before the Gorkha earthquake. So the main objective of my presentation is to update our understanding by adding the last few years of data up to now, following the same methodology of Dr. during his PhD work. it's not moving anymore. Yes. So first, one slide on the DMG seismological networks. So the historical network, the backbone network, is the one on the framework of the DMG DAS collaboration. We can see in red the network of the National Center of Kathmandu, in blue the network of the regional center. So this has been in function since 1994 and has enabled the DMG to carry out its principal mission, which are the seismicity alert for events greater than 4 of local magnitude, and to characterize the seismicity hazard, which is what interests us today. But since 2019, Nepal has started to develop other collaboration with other institutes, and what we can see it's other triangles in the map. And here we will not consider these networks because at the time of the Gulf earthquake they were not working. One word about the seismological workflows used at the centers. We have two different, one based on the DMG DAS stations, on which picking is manually done by the analyst. But since 2019, we have another workflow that incorporates all the stations of Nepal, and on which picking is automatically done, and the earthquake are automatically detected, and alerts are sent. So we can see here the region of interest. We will just look at the earthquake in the surrounding of the rupture zone, around which the fault steeped during the main shock and the aftershock of Kodari. We will only use the station of Central and East Nepal. Picking is manually done by the analyst, so that's a huge amount of work over 10 years. And the location method is by using Hypo71 program with some of the parameters written here below. So we can see here the result in terms of seismicity. In this figure we have the distribution, frequency, magnitude distribution, with the cumulative number of earthquakes with the magnitude, and the incremental number of earthquakes depending on magnitude. And if we take the maximum of this histogram, we access the magnitude of completeness, which is the magnitude above which we are sure that we are able to measure all the earthquakes. So in the following, we will consider only earthquake of greater magnitude. But this magnitude of completeness varies over time. And if we look at this picture, we have the concentration of earthquake over time from 2010 and 2025, depending on the magnitude. So we can see the Gorka earthquake and all the aftershocks, dramatic increase of aftershock just in the next few years after. And if you look at the end at now, we can see that clearly we have a larger amount of earthquake than before the Gorka earthquake. And the two curves show the two methods of accessing the completeness magnitude. And we can clearly see that there is a decrease over time. So that shows that we have a better ability to detect smaller earthquakes now compared to before. So here we see the cumulative count of earthquake over time for earthquake greater than 1.5. So before the Gorka earthquake, we had a seismicity rate of 92 earthquakes per year. We see the dramatic increase of aftershock after Gorka earthquake, and progressive decrease in seismicity rate, which is consistent to post-seismic relaxation models that we have. And now we have a seismicity rate of around 2,000 earthquakes per year. So the seismicity rate is decreasing. In 2020 it was several times higher, now it's less, but it's not it didn't went back to normal, and we think we would have to wait a few more years to get back to normal. Here we can see the map with the number of aftershocks on the region of interest. So we can see that the distribution is concentrated in the surrounding of the post-seismic slip during the main shock and the main aftershock. We see a narrow band just at the foothill of the Himalayas, and which is consistent with what was observed before the Boca earthquake. But as Laurent presented before, we have also some small clusters, new clusters, and especially the ones around Kathmandu. Even if the new aftershock that we measured are not located in this area, this cluster is now extinct. So the main conclusion is that the seismicity rate is decreasing as expected, as we saw, but it still remains higher than before the Boca earthquake. And thanks to location of the aftershocks, we can confront our results with geological structures, and it will be treated in detail by just after me by Gabriel and Karim. And I would like to finish by emphasize that the work we done at Nepal with the excellent peacekeeping work done at the National Center, 10 years of data processing of signals, and also by the maintenance of a seismological network over more than decades, few decades.
Very much. We will have questions, but first, please, could the projector change to the next slides, and as soon as they are up on the screen, we will start the next talk. In the meantime, we've got time for questions. Are there any questions on the talk? Great.
Thank you for your presentation. After long aftershock observations, what insights can you provide regarding potential future seismic hazard?
As I state, the distribution of earthquake was consistent and with, in comparison with before of earthquake, with the region at the foothill of the Himalayas. But as a lot of strains being displaced southward during the Boca earthquake, we saw that there is a high seismicity at the intermediate ramp around Kathmandu. So this is what Boca earthquake changed, but this is only in the region of Boca, and in all Nepal you have a higher risk of large and great earthquake in western Nepal, which hasn't seen large earthquake since like 6 centuries or so.
Okay, thank you very much. We're going to have to move on, I'm afraid. We're 15 minutes over. Change slides to the next talk, and then we have questions while it's changing. Okay, the next talk is by Lokvijaya Adhikari, again on aftershocks of the Boca earthquake. And after this talk, I'll hand over to my co-presenter, Subesh Kuamara, who will do the end of this session.
The two talks that were presented before this talk, and this will be about the aftershock of Boca earthquake and its relation with seismogeological segmentation of the main Himalayan crust. Just I want to start with this slide because if every large earthquake, devastating earthquake, this monument in Kathmandu has fallen facts and has been reconstructed every day. So already we have new tower after the yes, after the Gotha. When we talk about the Gotha earthquake that occurred in 2015, April 25, so it's nice to see the seismicity in the Himalaya before Gotha earthquake. So because there are many changes that we can see and there are many similarities that we can observe also before the Gotha earthquake and after the Gotha earthquake. If we look at the seismicity in Nepal, it is not similar all over the Nepal Himalayas. So in western Nepal it is diffused and distributed in wide area from mountain to the Shivali, let's say, in the line. And in eastern part, also the seismicity is very diffused and distributed over large area. But when we look at the central part of the Nepal, it is located just below the high mountains of almost 2,500 meter height mountain in a linear line that we can see here. And another interesting thing, so this is Kathmandu Valley. So just inside the valley, so this data shows the seismicity of 20 years. There were no earthquake, even of small magnitude, during that time. Even by mistake, any earthquake was not located in the valley. So all the earthquakes in this region were located just north of the area along the line. Then what happened to after the Gotha earthquake? So we can see all of the earthquake. Now the number is already the Theo mentioned. More than 55,000 of officers of Gotha earthquake has been recorded and processed, and those just lie in the around the rupture of the Gotha earthquake. So let's have a look. There were some clusters even in Tibet, South Tibet, and after the Gotha earthquake, some of the clusters were disappeared and some new clusters were seen after the Gotha earthquake. And there was one talk by Chaudi because the Gotha earthquake triggered, so the Tingri earthquake at that time of the 3 hours of the Gotha earthquake. So here, just we see the rupture of 2 meter by green line, and the black line shows the post-seismic slip. So there are some prominent clustering of the earthquake in a different region, and most of the aftershocks were concentrated in the region, and the number of earthquakes maybe were less than what we recorded before the Gotha earthquake, just following the Gotha earthquake. Now, when we look at the dots of the center of the Gotha earthquake, they are not distributed or located homogeneously. We can see some changes, and these changes are related to, so we want to see if these changes are maybe related to the structure beneath the region. So the main structure is main Himalayan thrust, and we want to see the relation of these earthquakes with the structures, main structures and auxiliary structures that occur beneath the region. When we look at the aftershock, so I was talking about the Kathmandu. So after Gotha earthquake, so there were many earthquakes occurred where there were no earthquakes in the past. So the south of the previous permanent seismic area. So we have two clusters. That was the one was located here by Kathmandu Valley, and another one the east of Kathmandu, which follows some geological structures of all beneath the area, because there is no fault, we cannot see, maybe that follows the fault in adjacent area. And there are other seismic clusters that are occurred in the north of the permanent or the previous seismic line, seismic line. The one is Himalchuli that occurred after 2 years of the Gorkha earthquake, and Sisapangma that was appeared just after the Gorkha earthquake. So basically now we can differentiate all the aftershocks or the seismicity in this region in 3 regions. So one below the permanent seismicity line, and one the north of the seismicity, permanent seismicity line. And another thing we can see that the density of the events are not similar in the region. So in the westward, near the epicenter, the seismicity is diffused and it's less, and in the east, the seismicity is very big. So we have two big, the main shock and the largest aftershock of the Gorkha earthquake in the extreme point of the rupture area. Then so we can easily observe and see and allocate the region with green rectangle shown in the figure in different zones. So I will show some result of the cross section of the two area here. So how it shows or locate below the surface in main Himalayan structure, in the structure. So this is the time series of time sequence of the Gorkha earthquake and its aftershock along the longitude. This is the main shock. So this is the days from the main shock that occurred in April 25. So we see that there are some organization of aftershocks along the longitude. So this shows the variation in the MHD, the structure below, the controls the occurrences of these earthquakes in place, so along the longitude. And surprisingly that we were talking about the new seismic clusters that occurred just 2 years after the Gorkha earthquake. The more than 9,000 earthquakes were recorded below the magnitude of 3, almost 3. And this seismic swarm was not observed by the people or not experienced by the people. Similarly, so the name of the clusters that we discussed in the previous slide are labeled here, and these are the clusters and the seismicity, which shows the some segmentation in the area along the longitude. So by this, so we divided 5 seismic zones in the region of seismicity region by green rectangle, 2 seismic zones in the south by red rectangle, and 2 seismic new zones in the north of the Kathmandu. This is also the time structure of the seismicity after the Gorkha earthquake. So we see that the aftershocks were declining or decreasing rapidly just following the earthquake in each region, in each zone, in each cluster. But there is one area where there were no earthquake before the 2017 or this crisis occurred, but that occurred in 2017. And that stopped for some time and then reoccurred next year, and that followed by 2 more years. And this crisis is already published in Frontiers. The detail of the analysis of this earthquake can be seen in this paper. So I will not talk about this now. So now let's have a look. So this is the updated figure with all the aftershocks that were occurred in the last 10 years, and the cross section is taken from the Hubbard record 2016, and now we see that the most of the earthquake are located at depth at the upper part of the down the end of the ramp in the north, and similarly in the new cluster below the Kathmandu near the ramp also in the. So this is we see that the seismicity is located near the ramp and the structure that we have already identified. Similarly, the density map shows the cost of the earthquake. These are located just in the structure in amnesty, and some in the downwind of the ramp in the just a little bit above the ramp of the structure. Similarly, in Chile, so this follows all the earthquake located at the downwind of the ramp that is placed a little bit down compared to the Kathmandu Nepal cross section. The earthquake are a little bit in the depth of the earthquake are more in this region. The balance cross section is taken from the ceiling 1992. It shows that it confirmed with the existing the structure that we already have. So this shows the density map of the same cluster, and every dot is every square kilometer. So at last, just I want to show this is the density of seismicity in the area, and this is the offshore density, and these yellow dots are the blue dots are the high frequency drops that were recorded in the area. So we can see that the segmentation of the region can be observed before the earthquake during the interseismic period that follows the post-seismic and the post-seismic period. The more energy are located in every patch of the region. So this shows that we can predict, maybe this will help to understand the hazard in the area. We can predict the area where the rupture can propagate and at the high energy after the earthquake occurred in that region. So this cluster shows the similar pattern of the seismicity rate before the earthquake and after the earthquake. So we can know with data if we have the recycling the seismicity.
Thank you very much indeed. Please change the slides for the next talk. In the meantime, if there are any questions. I have a question.
Okay, thank you very much for the nice presentation. I have a small question regarding Isapanga cluster. Since it is quite north compared to the network coverage, so how did you locate this? Have you used station from China?
No, all the operations that we have displayed here are located by our network. So there is a very large azimuthal gap that we know. So this is just to show there were some new clusters that were occurred in that area. So that doesn't mean this is the exact place. So there may be many,
Okay, in that case, do you think that this cluster can sit down in the south if we have a good coverage of the network?
So we have to work on it, but if we have the network that covers the cluster, maybe it is located a little bit north south.
Okay, thank you.
Okay, thank you very much. We have to move on to the next talk. We're running out of
Thank you very
time.
much for the presentation. I have just query about the temperature pattern in south of Kathmandu or around Kathmandu. I think around the Kathmandu there is active fault. I think this was published by VIII et al. Active fault around Kathmandu. So I was concerned about seismicity around Kathmandu. So I think the mechanism of this event is related to rivers or this is called reactivated.
There are many earthquake with different mechanisms, which like with normal and you can see, but most of the major earthquake in the region are rivers.
South of that.
Even in this.
Okay, thank you very much. Next talk is by Marian Carlos. Your time is 15 minutes.
Thank you very much. And I wanted to thank all of the conveners of the session as well as the conference for organizing a lot of really excellent presentations and discussions. I'm a professor at the University of Texas at El Paso. And I'm going to be talking today about, it's related to the talks that you've been hearing. I'll be talking about aftershocks of the Gorka earthquake. But I wanted to highlight that the aftershocks that I'll be talking about are from a temporary deployment, where we brought 46 stations into Nepal, collaborating closely with the Department of Mines and Geology, as well as other groups here in Nepal. And we installed these stations about 6 weeks after the Gorka earthquake, and they were out for just 11 months. And so this talk is really showing you some of the data and the potential of that type of short-term seismic network to look in more detail at situations where you have a dense aftershock sequence or a small cluster of seismicity that's in need of further study. So I mentioned that I'd be talking about that aftershock deployment. So we deployed the instruments in 2015-16, of course, right after the Gorka earthquake. In 2018, we came back and hosted a seismic data processing workshop. By that time, the data was publicly available online, and it's still publicly available online now. And so if any of you would like to work with those data, you can access those in the EarthScope Data Center. And you can create your own earthquake locations and work with those data. In 2018, when we came here, we worked with many people in this room, as well as others here in Nepal, and talked about different types of seismic data processing that we could do with these data. And then, so I highlighted a few other things. We've been publishing papers with the data together with students working with these data sets over the last several years. Several students just graduated over the last few years with their PhD, including my student Mohan Pant, who was very involved in this project from the beginning of the deployments. And we're still working on a few papers. I wanted to mention also that, so in addition to the pandemic making it difficult to return to Nepal over the last 7 years, I haven't been back to Nepal since 2018, unfortunately, although I really loved working here. I hope to work here more. I also became involved in an environmental seismology project in Antarctica. And I mention this because Antarctica is a continent that really is, should be accessible to the entire world. And it's a place that is very relevant today with climate change and that will have impacts across the entire world, as well as in many parts of Asia affected by sea level rise. And so this is what it looks like to pick up a broadband seismometer in Antarctica after 2 years that we had it deployed in the field. And it's quite different than picking up a seismometer here in Nepal, but we had to dig these big ditches of snow to get our instruments back. And I wanted to also mention, in 2018, when I was working in Antarctica, my student from Nepal asked me to bring the Nepalese flag to represent Nepal in Antarctica. And then in 2024, my master's student, Yishe Selden from Bhutan, was the first Bhutanese scientist to work in Antarctica. And she did an incredible job collecting seismic data and working in Bhutan. She's now a PhD student in Southern Methodist University in Dallas in the US. And so these are some pictures. The other thing I wanted to highlight before I get into the data and the aftershocks is I wanted to highlight that the Gorka earthquake, as many of you know, inspired a whole generation of students who experienced the earthquake here in Nepal and who saw directly the consequences of that. And I know many students who are just getting their PhDs now from Nepal who experienced the earthquake, as well as who've been getting PhDs over the last 5 years and who will continue, for whom the earthquake really made them want to help the country of Nepal, made them want to understand earthquakes in the Himalaya. And I hope that those students, as they're graduating, can find careers that are fulfilling and that they can give back to their communities. as I know so many of them who told me they were really motivated. They wanted to help understand earthquakes from after this very tragic event in 2015. And so the rest of my talk, I'll be talking about the aftershocks of the 1-year seismic or 11-month seismic deployment. And you'll notice a lot of similarities with the great work being done by the French groups and by the DMG here in Nepal. And as I mentioned, we're just looking at this temporary aftershock deployment. So the black triangles here are our seismometers that we deployed. And in this map, you can see the yellow dots are the, so these little, or sorry, I said yellow, I meant orange. The little orange dots are the basic seismicity locations from this 11-month deployment. And that's before we relocated them with HypoDD, which gives us a better constraint on the data. And our overall science goals with this project were to understand better the details of aftershock seismicity by putting out this temporary network of 46 stations, to understand the geometry of faults, the composition around the faults, the rupture propagation and segmentation, and then to support and work together with the Nepalese colleagues on better understanding what happened in this earthquake and the potential for future large earthquakes. And so I just summarized here on the right the steps that we went through to create this catalog that's shown with the little orange dots, those seismic events that are overlaid on top of the rupture area that's shown by the colors. In the interest of time, I won't go through all of these, but we went through a fairly standard method for locating these events. And then again, I just removed all of the other background colors. This is showing you just the events before HypoDD. And then here's in blue are the events after HypoDD. So you can see that these are a little bit better located events, a little bit more tightly following various structures. And if we then, so this type of aftershock data set, even from just these 11 months, tells us a lot. It tells us there are very few events in the south of the rupture area. You can see, as has been shown by previous talks, that there's fewer events in the western part of the rupture compared to the eastern part. You can see these little gaps and jumps in seismicity. So this cluster that's been already talked about today, and basically there's a wealth of information here within the seismic events, both in the data that you can see just in these 11 months after the earthquake, as well as in the data you can see after 10 years. Each of those tells us really important different information. And one of the most interesting parts, I thought, of the seismicity here was the structure that we can see in the seismicity in the eastern part of the rupture area. So I'll talk about that a little bit more. And if we look at these cross-sections, this is stepping from west. This is along the high climb profile, which was a previous seismic deployment. That actually is shown on shown by these little. This is the high climb line crossing through the rupture area. The very small triangles there are showing the seismic stations from that previous deployment. So in that region, we can see these kind of two clusters of seismicity here, and you can see the structure of the MHT from those previous work along the high climb line. And then with these other profiles, we're showing just east of Kathmandu. So what we see in the seismicity, and this is just the seismicity near this area, and then near the eastern edge of the main shock rupture, you can see is the most complicated structure. And this has already been mentioned today, but we thought that this structure looked somewhat similar to the work by Host Fullimer and the Laurent Beaumarchais group in France, working with the Nepalese colleagues, and where we see this possible tear fault structure north of Kathmandu, and a back thrust structure as well. And so these were some of the notable results from the seismicity data that we derived. And then finally, I just wanted to briefly show some tomography that we did with the local earthquakes. And this is a method that allows us to get P-wave and S-wave velocity models across the area where we have earthquakes. So the models are best constrained where we have a lot of little seismic events, and then less well constrained along the edges of the model. And I know this is very small, and I won't spend too much time on it in the interest of time, because I know we're short, but I'm happy to talk about this more with anyone later on during the meeting. And we basically see some interesting changes in the structure along strike, as well as velocity increases near the edges of the rupture. That's been seen also before, for example, in Ling Bai's paper in 2019 with colleagues. But this is work by my PhD student Mohan Pant, who just finished a couple of years ago his PhD, and we're still continuing to kind of look through in more detail at what is evident from these velocity models. So this is P-wave velocities on the left, and S-wave velocities on the right, the depth slices. And then you can see some cross-section slices. These are all P-wave velocity, north-south slices through the region. And then this is the S-wave velocity, north-south slices through the region. So in the interest of time, I won't go through all that. So I summarized some results from the aftershock seismicity and the structures that we see from that, as well as some initial interpretations from the tomography models, which we're continuing to refine and working together with our group. And so I would be very happy to talk with anyone more about the seismicity or the tomography models as we're putting all of those together into results. And I want to thank everyone, and I'm happy to take any questions if there's time.
Thank you. We can take 2 questions.
Did you try to look shortly to the older ancient earthquakes like Holocene age, for example? Because in the surrounding of Kathmandu, Dr. Gary and his co-author published some papers about the seismites we found in the teeny village in Kathmandu Valley. Absolutely perfect record of the seismites of the Holocene age. Did you try to look something? The seismites. Seismites, very characteristic sedimentary feature, which occur in between the parallel beds, never moved tectonically, for example, but in between you can find some zigzag shape, absolutely perfect, visible firm ground, firm sediments as the result of the shock of the seismite. And that's why the reflection of the earthquake most probably almost surely stays. That's why the seismites are the perfect record of the older than recent, in this case, Holocene.
I think that you've given a great suggestion to look more at those and to compare them with the results. I think we probably can't, so with the velocity models that we're creating, we probably can't resolve the very near surface structure, but I'll definitely look into the paper that you mentioned.
Maybe one more question. Yes.
Based on your findings, what key variation, crustal structure, discontinuity did you observe in near MHT?
Near the MHT, the question was what structure did we observe near the MHT? And as I highlighted, so I think the most interesting part of the results is the structures that appear to be highlighted by the seismicity, especially in the western part of the rupture. And so the things that I highlighted along the lines of the models from Rose Host Polymer's paper as well, and from the French group, the idea of the back thrust and the tear faulting were some things that came out of the seismicity. And then with the velocity models, it's a little bit, we're still refining a little bit the resolution in a few areas. And so, but in general, we see some velocity change near the MHT, but we're we're trying to get some better resolution on exactly the depth of it. So are these features we see in the velocity models right at the MHD, or are they right below it, or are they right above it? Is something we're still working on. Thank you.
My topic is variation of metropolitan of in the central Himalayan region and nearby regions. My research based on historical background. Alright. About 50 million years ago, Indian plate and Eurasian plate collides, and due to pushing each other, Himalaya is formed about 2400 kilometer, and Nepal Himalaya lies in the central part, called also Central Himalaya region, and the region consists of MC axes, MCT, MET, MMT, and along with these faults there are too many cross faults, and the figure shows the seismic clusters in the central Himalaya region, and most of the clusters are between 0 to 40 kilometer range, and the youngest lies at the average of 40 kilometer from the surface. Therefore, most of the earthquake lies above the youngest. And I have divided the central Himalaya region into three parts: western, central, and eastern regions. And along with major faults, there are some cross faults. These are the faults around the Gorkha earthquake. I have mentioned some Jodi faults, Kathmandu faults, Asle faults, Motihari, Gauri Shankar faults, and Motihari Everest faults. These faults start further address passing of adjustment to other regions from the Gorkha earthquake region. Log n A minus here. This is the Richter relation, and where there is total number of earthquakes, and A and B are 60 parameters. Mainly seismicity depends upon B parameter. B depends upon stress distribution. If B value is smaller, we consider the region as a higher seismic inner restored region, and if we see the spatial distribution of B value, then if the B value is different changing, then we consider the structural heterogeneity of the region. And if B value is smaller, we consider the larger, we accept larger magnitude of it, and if B value is higher, we accept small and greater and frequent number of earthquakes. And it also shows if the B value is decreasing, we consider the region is fault majority region, and the faults is being prepared for next event, and it also represents factorial density. And A value represents when B would be equal to m equal to 0, then n equal to 10 to the power 8. That means m represents total number of expected earthquakes in the region. And its the B value can be found by maximum likelihood distribution using formula B equal to log e by MAB, MC minus beta M by 2, where M is average magnitude, MC is magnitude of acceptance, and del M is magnitude range mean. Usually we use 0.1, and factors. If we take a stone in a hand, and the stone can be considered as a small part of the mountain. Such a fineness of nature we call factors. A line is one dimensional, and plane area is two dimensional. But if we consider the clusters of earthquakes in the surface, these are non-linear, and these such we find them measured by factor dimensions, and these factor dimensions lie between 1 and 2. And there is example of non-linear dimensional factors, and we find factor dimension by using first finding correlation dimension, equation 3, where n is total number of events in a region, and xi minus xi minus x represents the relation for pair points between I and j, whose magnitude lies inside R. If it exceeds R, the value goes to 0, and if it becomes less than R, its value becomes 1. In this way, it gives CR magnitude, and then plotting between the log R and log CR, we can find factor dimensions. It is just so. And using ISC, International Seismological Center, Nepal Earthquake Center, and USCS, and from other published literature, I downloaded about 10,500 clusters and used Pythons and MATLABs for the calculation, and I will find DC value 1.89 for region A, 1.76 for region B, and 1.585 for region C, and D value similarly 0.68, 0.60, and 0.63 for the region A, B, and C. The D value is obtained for all the regions except region acceptable for the region where dominant nature of the fault is frost type. Usually for frost type, B value remains usually less than 1, and the higher DC value shows for all regions. On higher epicenter shows that higher irregular or diffusions of epicenters. And plotting spatial factor dimension and spatial B value, and finding the correlation between them, it shows that for region A, B, C, there is a negative correlation between them, and for region B, there is a correlation more is stable. And the negative correlation between B value and spatial factor dimension shows that for a larger earthquake, the number of earthquakes clusters will be scattered in the region. Then large area will be affected. And these are the magnitude for frost faults. And 30 faults shows that the B value increases up to 0.97 during the Gorkha earthquake, and Kathmandu fault. If there is a cyclic, vigorous cyclic change in a B value, it increases from 1.1, 0 to 2, and minimum becomes 0.55. And for Motihari, Gauri Shankar faults, B value increases up to 1.22 and minimum becomes 0.42. And similarly, for Motihari Everest fault, B value there is a less irregularity than others, and its value becomes 0.74 to 0.67, and then becomes stable. Conclusion: the distribution of epicenter on large surface area could be understood by the high spectral distribution. We get high correlation dimensions and high value. It shows it is a lower earthquake, higher magnitude of the earthquake with this cluster will be scattered in a more region, and temporal variation of B value along the faults was reported from 0.85 to 0.94, which is less than the average global average value 1. It shows enough fluctuation during the period of April 25 to May 25 during Gorkha earthquake. In these faults around the Gorkha earthquake, there is enough fluctuation in the value, and then after some time, after May 25, it appears to be stabilized. The B value around 2.0 observed in the Kathmandu Valley of the maximum value, and they correspond to the earthquake storm during earthquake period. Announcements.
Hello, thank you. Thank you for the presentation, and I have some queries about this. And you have taken the value of individual fault. one query is for individual fault, and you see the event of whole area. So what is the duration of this fault? It also affects the duration of each fault and the duration of this fault. Data.
I consider the data from which are available for me. I get the data from 1964 to up to date, and for the Gorkha region, I consider the data for the after Gorkha earthquake, and to find the value for the region of the faults, cross faults. I consider the length of the faults from from previous literatures, and consider the width as average width 20 kilometers. Then find around the area, and I only consider the clusters which are inside this area and find the deviation.
And in Kathmandu, how many years the data include here and what is the source?
Only to calculate the value, I consider the data of the after the events.
Thank you, Professor Paul. Now I invite Kathmandu Nepal for his presentation.
Today I am presenting my presentation topic is recent seismicity in Western Nepal. So this is my outline of research work. First one is seismic network, and I will discuss about the geological structure of Nepal Himalaya. And third one is key data that we recorded in our institute. And fourth is seismicity in Western Nepal from 2020 to 2024. And fifth is Bhutan relation with our big data. And then I conclude this research work in conclusion part. So first one is seismic network. So you can see here. You can see here, this is our seismic network in Nepal. So we have two data centers in Kathmandu, National Optimum Research Center, Department of Mines and Geology, and another Research Center in Nagar Circuit. So this is the seismic network of Nagar Circuit. So we have 42 seismic stations. So this is the geological structure of Nepal Himalaya. So you can see here, this is the geological structure of Nepal Himalaya. So I will just talk about the western side. And in this figure B, you can see it here. And this is the paper which has been done by Laboratory year 2021. And they use the data from 2014 to 2016. And I just like to show the cross section of the western side. As you can see here, is the W2, W1 dash, which is located around the Bozang area. And you can see here, you see, this is the cross section of this area. And I just like to highlight, there is the MSD geometry. You can see there is the flat and ramp and flat. So in this paper, we state that the seismicity is controlled by one ramp in this area. And on the other hand, there is one cross section in this E2 dash, which is around the Pardani progressing. And you can see here the figure T, the cross section of this area. And they found that there is two ramp of the MST, and seismicity controlled by the two MST. As you can see, there is flat ramp, flat ramp, flat and ramp. So that's why seismicity is controlled by two double ramp instances. This is the geological structure of the western side. So today I am presenting the earthquake data that we recorded in our institute. So we have two processing software for the monitoring and distribution of earthquake data. First one is Geological, and second is Storm. So in this table, I just present the data that we recorded in our institute 2020 to 2024 of 4 mine events. The first one is Doti earthquake, and its magnitude is 6.6, and we pick the B phase and S phase 13 number. And after that, that Basra earthquake, its magnitude is 5.9, and we pick the B phase 16 and S phase 16. And Basra earthquake, its magnitude is 6.3, and we pick B phase 15 and S phase 15. And finally, this is the Jasper earthquake, and its magnitude is 0.4, and we pick 14 B phase and 14 S phase. And here I just want to present the data that we recorded in our institute. First, I will just do so the total earthquake. You can see here we recorded 737 number of earthquake events. That includes the events of an episode. And similarly, Bhadra earthquake we recorded 358 number of earthquake data. And moreover, in Bhutan earthquake we recorded 734 number of earthquake events, including the events of an episode. And finally, Dazapur earthquake we recorded 766 number of earthquake events during that period. So I just brought this data into that presentation. You can see here in figure 10. So in this slide, I am presenting just the epicenter distribution of the rupee earthquake in figure 8. You can see here. This is the measures, and these are the epicenter distribution. And this epicenter distribution states that it indicates from the extent from the northeast to southern direction. So similarly in Basra earthquake, this is the main sub, and after distribution indicates that it also extends from the northeast to southern direction also. Similarly in Bazan earthquake, we can see here is the main sub, and after clustered around here. So it seems like training is east to west direction somehow. And moreover, finally in Dashboard earthquake we can see this is the main sub, and after the kind of standard distribution listed that it extended from north to south direction. And in this slide I present the seismicity of Western Nepal from 2020 to 2024, and during that period we recorded more than 3600 number of earthquake events, where we recorded 3 magnitude, which is greater than 6 magnitude, and we recorded 11 number of earthquake in range between 5 to 6 magnitude. And similarly, we recorded 74 number of earthquake in range between 4 to 5 magnitude, and we recorded 481 number of earthquake events in range between 3 to 4 magnitude. And lastly, we recorded more than 3,000 number of earthquake events, which is less than 3 magnitude, and we brought this data only to present the graphical form. You can see here the figure 6. And this is the seismicity of Western Nepal in between 22 to 2024 data. And you can see here most of the earthquake cluster overlies around the MCD. And this is just focal mechanism of the board for them and to the earthquake resource from the USDS. So this is the cross section that we just crossed the plot cross section from A to AS, just formed like this. And similarly, you can see here this is the epicenter density map, and I just want to show you about the. You can see this is the Bajura and Bazar include area. And somehow we found some epicenter cluster around the lake area, and this is the Dashboard topic, and I just saw this data in graphical form also. And in this slide, I just want to show the Gutenberg distribution of earthquake data that we recorded 1994 to 2024, which is recorded in our institute. And we found the MC is 2.5 here, and P value is 0.72. And in figure P, this is the histogram, and most of the earthquake ranges in between upper range in between 2 to 4 somehow. And this is the earthquake data that we analysis from the data from 22 to 24, which is recorded in our institute, and we found the same data like CMCC 2.3 as the previous one also, and P value is 0.75, and this is the histogram that we got in this figure. And this is the control section. So during this period, we recorded 4 minor earthquakes, and we calculated the MCC 2.3 and P value is 0.75, and we recorded more than 36 data of earthquake events during this period. And this is the just I want to show about the MST condition in the western part. In the western part, there is single dam and double dam also. So my research question or further to study the research question for the first is what type of dams is used for by especially around the area. So this would be one of the questions or research area to analysis of the MST and to understand the sensitivity of the area also. And thank you very much.
Okay, then we can go forward. Thank you, Dr. Balwani. I invite Dr. Dhaka for his presentation. Analysis of the main Himalayan fault system based on 2050 quota and 2023 target.
Namaste and good morning, everyone. My name is Sanjeev Dakal, and I am doing PhD in Institute of Tibetan Planetary Research, Chinese Academy of Sciences, under the supervision of Professor Ling Bai. So today I am going to present about the analysis of main Himalayan thrust fault system based on the 2015 Gorkha and 2023 Jharkhand earthquake. Okay, this is my today presentation outline. Okay, let me start from the background. The main Himalayan thrust is defined as the detachment that separates the under-thrusting Indian plate from the overriding Himalaya orogeny. The collision of the Indian plate and Eurasian plate caused the Indian lithosphere to subduct, forming the main Himalayan thrust. This fault is the top boundary of the subducting plate or hotspot for the intercontinental earthquake and key driver of the Himalaya uplift. And this first figure shows the tectonic background of the Himalaya region, and second figure shows the historical outlook occurring in the Himalaya region, and third figure shows the main fault line in the Himalaya region. And main Himalaya thrust fault firstly proposed below the lesser Himalaya region and further identified below the K3 Himalaya region. And the main Himalayan thrust is complex structure, so it shows the along strike variation and across strike variation. So I am going to talk about the 2015 magnitude 7.8 Gorkha Nepal earthquake. And after the 2015 Gorkha earthquake, there are a lot of study has been done. This figure shows the distribution of the earthquake after the 2015 to 2020. And this figure shows this figure studies the microseismic study in the source area and find out the main Himalayan thrust took place structure. And after the 2015 earthquake, we also study about the Gorkha earthquake, and here we can see that the station we use for this study. And the main Himalayan, from our study, we can say that the main Himalayan thrust is not simple fault, but a complex system with ramp, tap, and lateral variation that control the earthquake behavior. The lesser Himalaya, ramp, and duplex are critical features that influence the stress accumulation and rupture dynamics. The 3D geometry of the main Himalayan thrust is essential for improving seismic hazard assessment in the Himalaya region. And this is the map view of this is the cross section of the source area, and this is the western profile of the profile CC, and this is the eastern profile of the profile CC from the map view from the cross section. And here you can see that the lesser Himalaya ramp in the western profile, and most of the offices are located above the main Himalaya thrust.
And in the western seismic source region, the Indian lithosphere subduct at nearly 5 degree beneath the Himalaya, and with nearly 10 degree ramp beneath the lesser Himalaya, acting as the earthquake rupture initiation point. In the eastern seismic source region, a high velocity crustal body linked to the Patna Fault and Pinga Amateur Drift system stop eastward rupture propagation. And the main Himalaya thrust, the geometry segmentation and 3D structure variation control earthquake rupture length. And this factor highlight the role of subduction interface complexity in the Himalaya seismic behavior. And after the 2015 earthquake LRST debate about the seismogenic zone, so some researchers find out that most of the aftershocks are located above the main Himalaya thrust, and some researchers find out the most of the aftershocks are located below the main Himalaya thrust. That's why we want further study about the Gorkha aftershock. So for the Gorkha aftershock, we use the continuous waveform data that was derived from the IRIS Namaste seismic network to study the aftershock, Gorkha aftershock. So this is the example of the continuous waveform, and these two are the detected event. And for this study, this is our workflow. So for this study, we use the raw continuous waveform data and auto picker for the phase picking, and real rapid earthquake association and location for the association, and then finally we did the hyperdegree for the relocation, and we got the complete catalog. And this is the travel time versus hypercenter distance of our detected event. And this is the magnitude of completeness. Our magnitude of completeness is 2.6. And this is the spatiotemporal distributions of event. So this figure shows the temporal distribution of the event which follow the Omari law. And this figure shows the spatial distribution of the event from the detected catalog. And this figure shows the spatial distribution of the events after the rapid earthquake association and location. And this is the distribution of the event after the hyperdegree. So the relocation of the detected event and the cross section of the source area. Here seen that the orientation and location of the cross section provide a clear spatial overview for the seismogenic zone and the role of the main Himalaya thrust. And the cross section is statically placed to the captured key structure feature, including the main Himalaya thrust and the distribution of the seismic activity. And this is the cross section profile of the previous map view. And here we can see that the cross section reveals the depth distribution of aftershock along OO profile, predominantly concentrated above the main Himalaya thrust. And the shallow depth of this aftershock within 20 km aligned with the seismogenic zone, where the crust is most prone to the retired failure. And main Himalaya thrust shows the noticeable lateral variation along the strike with lesser Himalaya ramp beneath the main strike area. And these are the across strike profile of the previous map view. And here you can see that the most of the aftershock are located above the main Himalaya thrust, which is aligned with our finding from the earlier study. Okay, after still we are working on the aftershock of the Gorkha earthquake is completed here. So after the 2023 Jadarpur earthquake, we will study about the western part from the Gorkha main shock. So this is the seismotectonic background of the 2023 magnitude 5.7 Jadarpur earthquake. And for the 2023 Jadarpur earthquake, we use the waveform modeling and the relocation for the main shock. And we use for this study we use the crustal 1.1 model, and we use the waveform data from IRIS and the seismic station we developed in Nepal and southern Tibet for the relocation. So this figure shows the station that we use for the waveform modeling. And for the relocation of the main source, we use the station of global network, that is 0 to 20 degree, and with station in Nepal and southern Tibet that we developed. And this is the peak of this is the travel time versus the epicenter distance from our peak off, and these are the two example waveform of the peak off, P waveform and S waveform peak off. And this is our main result from the waveform inversion. Our result indicates that the focal mechanism of this orbit is thrust-forward type, and the magnitude is 5.7 with 13 km depth. The raps are propagated along the deep direction towards the shallower depth. So, which was the main cause of our severe damage of in the western the Jajalpur earthquake, despite the earthquake being of moderate magnitude. So the rapture length is about 25 kilometers along this side and 20 kilometers along deep direction. And we also compare the main Himalayan thrust fault from the previous study, and we just juxtapose our result location in the western Nepal main Himalayan thrust fault model. And this is the slip distribution map, and intensity and the relocation of the Jajalpur earthquake. And from this presentation, we can say that we conclude that the 3D geometry of the main Himalayan thrust exhibits significant variation, forming the flat band structure. Its hanging wall features are high angle faults, with the footwall consists of the northward thrusting, thinning Indian thrust, and collectively forming the main Himalayan thrust system. A key factor is in the earthquake rupture and plateau of it. Major earthquake can occur on the main Himalayan thrust, such as the 2015 magnitude 7.8 Nepal earthquake, or duplex or dams as seen in the 2023 magnitude 5.7 Jajalpur Nepal and 2005 magnitude 7.6 from Kashmir earthquake. These are our previous work after the 2015 Gorkha earthquake. And thank you. And last one information from the Earthquake Science Journal. They are going to publish special issue. So if you are interested, then you can visit the website. Thank you.
Okay, so then we go forward to the final presentation of this session. Thank you, Mr. Sunil. I would like to invite Shiva Sueli for the presentation. Analysis of aftershock activity of the 2023 Western Nepal earthquake.
Okay, good morning. Thank you. I believe you still have more 15 minute motivation to listen to me. So, I'm presenting the analysis of the aftershock activity of the 23 Western Nepal earthquake, the Great Blue earthquake in 23, Bozan earthquake. So, here are my outlines. I will start with introduction and I will discuss why temporary network installation is needed for these reasons. And I will show you some very fast results and discuss about the future plan. So this is the map from the Lopizet et al. So you can see this is the map just after the 2015 earthquake. You can see the cluster of the earthquake in the center part. And in Nepal, most of the people their attention was in the central part of the country. So at the same time, there was an earthquake of magnitude 6.3 in the place scale program. And the second one just after a month in the Jajalpur. So you can see this the second map from the glaciers. So going back to the background, we know Nepal lies in a very active seismic zone, and there are a number of temporary networks to study the structure of the origin and the seismicity in Nepal Himalaya.
thanks to many researchers who did really nice job since some more than a decade or more than a couple of decades. This figure summarizes the image of the cluster structure until date, and regarding the construction practice in Nepal, we are very poor. So more than 40% of the buildings are made by only from the mud and stone. And only 10% buildings are accessible. Out of 10%, all of these are not perfect roads. So these results, we have the high hazard, we are very vulnerable, and these results assessment, very high assessment takes of the. So the big question to the Nepali seismologists and from the public and from the media is what is the solution to reduce the assessment risks? And the simple answer is you can start to educate people about the earthquake. And the complex answer is you can start for the earthquake early warning system and so on. So with this background, I saw there is a gap between the scientific community and the public. So with the objective of the education and the basic research, we started one project we called Seismology at School in Nepal in 2017. So this one example of the educational activities that we perform in the school department. In the right figure is the Nepali School Seismology Network station map. So at the same time, the primary goal of this project is to do some educational activities and to make people aware about the earthquake, to collect some seismic data. At the same time, we can use this kind of seismic data to locate local earthquake. We have one very strong evidence from the central part of the country. This figure is the earthquake location by this network in 2021. So we have located more than 250 earthquakes in this region during our 1 year period. And the interesting fact is that we have located 23 new earthquakes which are not in the national catalog. So you can see this magnitude of completeness is 1.8, and this is the very interesting result for us. And so we can use this kind of low cost seismometer for the study of the microseismicity. So following the same step, I'm working at the Nepal Academy of Science and Technology just after the Bazar in the earthquake. We went to the city center region with colleague from NEMRC, Dr. Lobje Adhikari, and for the purpose of installing some temporary networks, temporary stations, that is to the site. So for the installation of temporary sites, we defined the selection criteria. Of course, this should be in the center region. And since we are using the raspberry site, the availability of the internet and the power supply is the major part. And we want to go a bit far from the cultural noise. And we also consider the existing station from the national network to reduce the electrical gap. So top panel figures, you can see the damage of this whole house, and this figure is a symbolic figure of background noise from a specific station we installed after the earthquake. So from this figure I can say that this is a good candidate to locate local earthquake. And this is the map of the available stations in the region with published catalogs from NEMRC. So this is the theory. The question may arise: what is the benefit of adding this kind of low-cost station in the region? So I compared this. This is a case of Bazan. We have this black triangle are the station from NEMRC, and the green inverted triangle are how we install station. So if I assume there is an earthquake very close to the epicenter of Bazan earthquake, and assume for the maximum electrical gap, if I use only NEMRC station is about 170 degrees. If I add new installed station for this analysis, the azimuthal gap reduced less than 1. I think this is a very important point to get the better result in the location and to have a less error in the location of the earthquake. So another important interesting result from the temporary site is this is a 1 day data
from this station, which is installed close to Bazar swimming pool, you can see many earthquakes, different magnitude, many earthquakes. This is the one data. So this is not surprising for us because earlier studies from Laporte et al. In 2021, they already claimed that there is a cluster of earthquake. So from this diagram, from this one plot, what I can say is that the site selected by our globe is located in a good place. So we can locate it, we can take that many earthquakes. So it is the very fast result from my analysis. I am going this step. Okay, here you can see what is the workflow for me. I collect data, I pre-process data for the SESCOMP software. The SESCOMP software is maybe it is very new for the Nepali audience. This is the software which can automatically detect and locate the earthquake, but we have to go to verify. We have to go each and earthquake, each and every earthquake to manual relocation. So until now, I have collected data. I have filtered this data to give input for the SESCOMP and automatic location of using SESCOMP. Until now, I am using just only 1 month data, and these steps I have to be done. So from 1 month data, this is the seismicity plot. You can see the scatter diagram. You may have question because there is no cluster or there is earthquake everywhere. So what I have to do to improve this location is that I have to go to manual relocation using different models. So from this diagram, this is the 1 month period of the seismicity. Maximum magnitude I got is 6.4, which corresponds to the Zerpel earthquake. The minimum magnitude I got is magnitude 1. I am only using this green inverted triangle, which is the open data, which is the signal. I am not using any emergency data because this is not available yet. So the number of earthquakes per month is 135, and the most importantly, the average RMS value for the automatic detection is about 3 seconds, 0.3 seconds. I think this is good value. So here I am showing this magnitude time sequence for month of data. You can see the blue circles are from the NEMRC catalog, and the red circles are my own catalog. So you can see there is no earthquake less than 4 from blue circle. It doesn't mean that NEMRC didn't record magnitude less than 4. What it means that NEMRC get mandate from the Nepal government to publish or to announce the earthquake of magnitude 4 and 5. There are many earthquakes. If you heard the previous presentation from my colleague, there are many earthquakes from NEMRC. So the next step is that to be done is that I have to go in the same script, same workflow for the more data, for at least for 4 months of data. Okay, here are some future plans. So until now I am doing calculation using the automatic location in SESCOMP software. So the next big step is I have to go each and every earthquake to see the each peak and gas arrivals, phase picking, and to confirm this is good or not. If not, then I have to pick manually and relocate using different models. For example, there is okay. For example, this Hydro 71 linear loss in hyperdegree. So maybe this is a big question to all of us. If we can integrate data from NEMRC and this kind of low cost station, there will be better science result. But I don't know, practically I don't know what will happen. And I would like to relocate at least 4 months of data starting from October 2023 to January 2024 because our stations still there for 4 months. So collaboration with NEMRC is a big question. Maybe if we are lucky, we can get collaboration. We can do collaboration. Thank you so much, and here are my acknowledgements. I'm happy to take your questions.
Anybody? Questions? Any questions, please?
How many schools are involved?
Until now, we have installed seismometer in 33 schools in the central part of the country, and more 5 to 10 schools in the Kathmandu region. In total, I can say 45.
Do you have any plan to expand that coverage? And when there is a massive school system, geological survey is leading that. I don't know whether it can be continued. Do you have any connection with it?
I think extending this robust seismic network across the country is a very good idea. And we can teach people about where this is a kind of public outreach and activities. And we can, at the same time, we can use the seismic data for this kind of research, basic research. But what is the big problem for us is funding. So maybe there should be some funding available or such as well, but we are looking for funding. Thank you. There is one question. Monica ma'am.
Thank you, Dr. Suvedi, for your nice presentation. I really appreciate your work. You have been working since last 5 or 6 years, and you are doing a pretty good job. You concluded your presentation with the future collaboration with the NMRC. So I'd like to know what kind of collaboration you want from us.
With NAST NAST, which is government office. NMRC is also government office. And what I'm looking, for the moment what I'm looking is to share the seismic data to get better scientific result for Zazar in Badana. That's it for the now. For future plan, we can integrate this kind of local seismic data to an emergency domain, and we can use all of the available data for this kind of seismicity location or any kind of seismic research activities.
Let's discuss and we plan.
Thank you so much.
More damage occurs around the VIII rivers, around the center of the other. I think it is directly effect or it depends on the material used in taking out.
I think this is a good question in terms of local scenario. So I would answer in different solution. So damage was intense across the river basin. Yeah, there should be some kind of sedimentary effect because of the layer of the river. With the time, it is a thick layer of the river. That is one answer. Second answer is itself the construction practice, because in the western part of the country they are building house just adding stone and stone, nothing in between the stone. And we also see this topographic effect in Desert Road, because the distinct headquarters of the Desert Road, there was intense damage, there was topographic effect. So I think there are many candidates that can contribute. They contributed for this intense damage during the Desert Road.
So, okay, we can discuss this in
Thanks.
our tea break. So, thank you very much. And next session, thank you very much. Thank you all, sir. Thank you very much.